We're given molar concentrations here again. 1 liter is the volume. What I mean by molar concentration is equal to moles per liter. And that's what we've been given, moles of each of these substances in a 1 liter vessel or flask. This one's a little different. Initial begins. These concentrations are not at equilibrium. We can't just plug those numbers in to our equilibrium expression. The products here are. So we can plug them in into our equilibrium expression. So we'll have to figure out what the concentrations of the reactants are at equilibrium, because that's when this expression is valid. I'll show you a shorter way you can do this, but I'll use an ice chart here to help visualize. Copy this. All right, so in an ice chart, I stands for initial, C stands for change, and E stands for at equilibrium. We're given the equilibrium concentrations of the products, which are both 0.047, 0.047 molar for both of these. All right, it's kind of like not aligned. And the initial concentrations were given for the reactants, which is 0.1. 0.1. So that's what we're given. In the beginning, there are no products, so there's the initial concentrations of the products are 0. What must the change in concentration have been to reach this equilibrium concentration? Well, the change must have been 0.047 molar for both of them. The mole ratios of all of these are 1:1. So if the products each increased, all right, we produced this much. All right, we produced it. That means the reactants, what? They lost that amount. That much of it was used. All right, so we're going to use a negative sign here to indicate that. 0.047 moles in this case is used of the H2, and also the 0.047 moles of carbon dioxide is used. Let's just subtract those numbers. 0.053 is what the concentrations of the let me do one thing at a time. I'm trying to talk and write and saying that. 0.053 moles of hydrogen is left, and also 0.0, kind of running out of space here, I should have stretched, of the carbon dioxide. Now these are all equilibrium concentrations, so now we can just plug and play into our expression. Now the short way was, if you just saw that, well, this is how much was used, or that's how much was made of the products, and then use the mole ratios. Again, it was, you could have done this without the ice chart because they're all 1:1. If you're going to make this much of the products, they're all 1:1 ratios. You must have used that much of the reactant cell, and you subtract it from your initial. All right, but I think this was a better visual to understand what is going on. Let's calculate case C. So the equilibrium concentration constant is going to be the concentrations of the products, which is 0.047 moles per liter. I'm just going to square that. No, I'm not. I'm just going to write it again twice. You could square it. Or over the concentrations of the reactants. 0.053 times 0.053 for the carbon dioxide and 1 for the hydrogen. It's going to do 0.047 squared, or just 0.047 divided by 0.053 squared. All right, and we got 2 sig figs. 0.786. I'm going to round that to 0.79. And if you want to write that in scientific notation, it'll be 7.9 times 10 to the -1.